as we projected this. This is really good.
Oh, that's nice.
No, not you need this. Just now your opportunity.
Hang on, I'm gonna shut this down.
So your pay is going to go work that you transit because that would be the way. But in that department, I mean, you're looking at Milwaukee or Salt Lake City.
Can you hear me? Just nod your head. You can't hear it all. Can you?
You asked about the labeling the observations in this multi-dimensional scaling part. I can modify this node 15b a little bit, and you can see that actually put some of this here. This is revised 15b. Okay. This. Actually, I don't need to run variable important now. Right? So let's just. So I have this one, and then when you have this random forest run, after that you try to try to find the misidentified observations. So here we do just find the IDs for those misidentified plants. And in the multi-dimensional scaling, let me just do that. I think I'm going to skip part of this, so we just go directly into what we talked about last time. Okay. Here with this part. So here this is a part, the second dimension. We reduce our four-dimensional data into two-dimensional using multi-dimensional scaling of the result. And it looks like Setosa is clearly separated from the other two groups, except that here we have some these two groups that there are some overlaps, and we want to see whether the observation that we'll try to isolate this misclassified observation. In this MDS part, you can actually just save that into a, just something that's just kind of going behind the scene. Okay, when you do this MDS part of this random forest object, MDS part produces this part, but it also returns some value invisibly. But here, this is something. There's a function called invisible that usually none of this traditional graphics function has this kind of thing here. Okay? They actually the major task is of course produce a graphics, but then they also return some value. And the return value has a component called points, and actually this is just the x and y coordinate of your path. That's all we need. Okay? So that's why here I actually produce that part, and also at the same time extract this x y coordinates of this points. Actually, this is x coordinate, y coordinate of this the points of this multi-dimensional scaling the scale. Okay. And then we simply just need to identify this misclassified observations in many ways, of course. Okay. So I can use this. I can use these points, try to make it stands out
15B
with different color. I'm not sure how good you can see that. And here, these three are misidentified plants from the third one was what? Virginica, okay? And there are three misidentified plants here, 1, 2, 3. Okay? Because this rely on color scheme here. Okay? Excuse me. Original colors was color 2 to 4, so this is red, green, and blue. And R has this like this colors in you know, this is red 4, green 4, and blue 4 in darker color. We like to call it. So that's what happened here. I use a darker color on this three colors. Okay. So here these three darker colors will sort of capture the misidentified plants that I have shown here. But this is not the best way. Now we're going to use a different pattern symbol. Okay. Anyway, here you can see that these 3 points, slightly different color, right? They are darker. Okay. I hope that this can actually capture that. Okay. You can see better. Can you see better? Here? No, we're not. Okay. And these three observations are misidentified. Okay. I use a darker color for that. And if this is not enough to make this point stand out, then we can place a text next to it and explain that this is for one observation. So we can use this text command to do that. I still label with the same color. So hopefully they will stand out. Okay. So from versicolor observation 71, 78, and 84, these are 3 misidentified. Okay. Because these 3 points just go too deep into the other group, right? Okay. And likewise, you have these 3 observations. It's 134, 120, and 107. Especially 107. Okay. Last time I already shown you this. What was that? This we plot this outline measures last time, so you can see that. Okay, actually, this point stand out. So here observation 107 goes too deep into this group, right? So that's why you cannot separate according to this. I also did a little bit analysis on this. Of course, this is on multi-dimensional scale things, which should not compare this directly with random forest result. But listen, that give you some idea. Okay. Here first, I calculate the group centers. So I can do that, right? You have this whole bunch of points. You just average the coordinates. You get sort of in one way. This is one way of finding the center. Okay. So group center will be done by this command. Okay. The by function is built-in R function, so you don't have to rely on any packages in that. So here I basically figure out the centers for this. Okay, so I use the by function, and for those multi-dimensional scale points, I take those points, and then we're trying to calculate column means. Okay, on say separate groups of these 3 species. Okay. So actually, basically this will produce a column means for the first 50 observations. Those are Setosa, and here column means was the observation from 51 to 100. Those are versicolor and likewise. So you see this result. Okay. So here, this would be sort of, well, in one way, this is one way of calculating group center. Right? This is basically just geometric centers of these 3, according to Euclidean distance. Okay. So we calculate that distance, and then let's say I find this, and basically after you find these geometric centers of each group, then I basically look at those misidentified. Look at those misidentified identities, and we try to calculate sort of the square distance, okay, from individual observation to each center. Sweep is actually, this is very useful function, and it's very fast. So basically, you take a group of points. In this case, these are those misidentified planes. Okay, we take the x and y coordinates for those misidentified points. Okay? And calculate the distance. Well, in this case, I calculate square Euclidean distance. Okay? From the center, which is Setosa. Okay? So basically, what happened was this, okay? When I did that, like first one, this is like, here I have this xi, yi for those misidentified identity, okay? And I find the distance between these two and what?
Why? This is not true.
So basically, just find the square distance between this, right? You can use that sweep. Basically, what sweep does is like, it's just calculate this xi minus x0 and yi minus y0. Okay, for each row of that data set. And basically, just do the sum of squares. Okay, so that's will be a square distance. So we do this for all the centers. So here, all the points to the center for this Setosa group, and all the points to the center for versicolor groups, and do likewise for the other ones. So basically, this is what this distance. This will be the square MDS distance from group centers for this misclassified planes. Just show that way. Of course, remember this is for using multi-dimensional scaling. This is not directly okay. It's not the result is not completely identical to random forest result. Okay. Actually, you can see that basically you look at this square distances from this individual to the center, because we know that this 71. All these the first three observations are supposedly versicolor, right? Okay, but there's distance in this multi-dimensional scale is very small to Virginica. That's why they are misclassified as from Virginica, isn't it? Right? See? This observation is actually closest to the center for Virginica. So it's classified. Well, in a sense, you can say this will classify as a Virginica. So this is misidentified planes. And here, so is this one. So from 70, for this observation 78 to the three centers, okay, the nearest one is what? To the center for Virginica, right? So misclassified as a Virginica. Okay. And likewise for the other one, except for the last one. Okay. The last one actually, this is supposed to be Virginica planes, but it has a shortest distance to Virginica. So according to multi-dimensional scaling, this is not really misclassified identities, isn't it? Okay. All the rest. Remember, this is result from random forest, not from this multi-dimensional scale. This is only part of output. That's kind of interesting to look at this in this way. Okay? If you rely on this proximity definition of that, actually, we are not actually misclassified that identity. This plane 134. And in fact, if you look at this multi-dimensional scale, this is what was that? This point 134, right? Okay. Among the three misidentified groups is the closest one to its center, right? So that makes sense, right? Look at that. I think for this class notes, I only modified that part, so I'll try to mention that. And actually, here for this forensic class, I tried a different setting for that. Turned out differently. Let me. I kind of changed the seat. Anyone print this out before this, or I think I used a different seed before. Let me try this out. And this is about printing the variable importance in this conditional inference forest. Well, I should say this random forest using conditional inference trees. Okay? I think we've seen this before. Actually, what happened is that, well, the variable importance is supposed to be positive, but okay, the cutoff point is actually just lie on the smallest, the absolute value of this. I should say the smallest absolute value of the negative points. I thought I had done this differently. Maybe I changed back. I use other keys and find out it's just cut off somewhere. But here, all except for this, they are sort of, in a sense, significant for that. Okay, but probably not the sodium. Okay. And maybe with other package as well. Just this Smarty, for example. Well, I thought it's probably nice to experiment on this. And R has there's a package called for each. Okay. Now, if you have a computer, well, I have this computer pretty old. It's only run with 2 cores. It's not so good for sort of parallel computing. If you have like running like at least 4 cores, you can try to do this. Isn't this for each? You know, you can do that. You can do this random forest like four random forests run in parallel instead of running them sequentially. Of course, the time save is not just it's not important, right? It's not 75% safe because when you do parallel process, it's also required, you know, this transfer data and put the data, you know, in and out. Okay? So that's why you can try this out. And if you look at vignette of this package called for each, you can see that they also have a random forest example using for each. You can try to run this. If you have 4 cores computer, I don't know anyone got computers with 4 cores. So you got one?
I don't think so, no.
Is it dual core only? You have the 4 cores, right? You can try this out. Look at vignette of this for each. Okay, you can run random forest. Okay. So I kind of experimented a little bit on that and something. Of course, here the example what I put down here is this is overkill. You don't have to do it this way. Okay, but just show that if we run into these problems of say that some computation require a lot of computation time, and then given that resources allow your computer having like 4 cores or even 8 cores, what is anyone knows about what is the top in the line? What is that? How many cores we have for the computer nowadays? I saw in a commercial before this was 8 cores. It's like that. But you have 4 cores, right?
Yeah, not for laptops yet.
Okay. Or better yet, this for each package also allow you set up in this run your codes in parallel, using several computers linked together. So you have that. Okay. I don't have the resource to experiment with that. Not even for this. The best I have here is like only 2 cores. This is only 2 cores. Probably not enough to do that. Okay. Well, here in the following example, I kind of make use of the current date information as a random seed. Okay. So let's just explain a little bit, a few seconds about this date. Extracting date information. The first one basically this is a text string representation of current date and time. Okay. You can see something like this. The result is a text string. Okay. Curiously, the second one, although looks like it returned a text string, but it's actually a numeric value. I think this you also learned from science. It's a numeric value. So you actually can perform some operation on this, similarly text value there, character value. Okay? So here sys.date just return current date is of class date. Okay, this is numeric data values. Okay? But you can say, oh, okay, this is to extract the data for tomorrow, something like that, like this. Because internally, this is not what you see internally. Okay? What you see internal value will be something like this. Okay? You look at this one. Okay? It's a number, something like that. Okay? So here, this is number of days since certain time. Because you are coming from stars, you know some value, but this is not the case in this one. This is more. The day 0 is more following this international standard. So maybe wonder that is actually the quickest way to extract the information is, I guess you can do this. Okay? You can do this here as integers. So here this is date 0. Okay? Date 0 is 1970, January 1st. Celsius is 1960. But that's not a standard. It's not international standard. Anyway, for the computer package, they use a date 0 like this. I think this is like, this is POSIX date standards, I forgot. Any kind of international standard. So actually, I use the current date minus 15,652, right? So basically, give date back to date 0, right? This is date 0. Okay, this is sidetrack from what we are trying to talk about. Okay. Let me just include this for each. Okay. Yes, we already done this random forest. We already replaced that. Okay. Now let's take a look again about the iris data set. Suppose I set this the train set proportion to be 60%. So this is 60%, 40% split. Okay. So I set this up first. Okay. And we have the group size of this. Okay. This is P for group size. So we have 50 times P train. So anyway. And I have this value set, this is sequence from 1 to 50, because here, the data is quite regular in this case, right? The first 50 observations are for Setosa, the next 50 is for versicals, that way. So I have this sequence generated from 1 to 50, and you add 50 to that, that would be the index for versical. If you add 100 to it, that would be the index for Virginica. So it's quite regular, so that's why I can program it this way. Here I try to run this random forest twice, each time with a different seed. Okay? Well, here just show an example. Maybe you want to do it differently. So here I select 2 seeds. The first one, I'm going to have a seed like 15,652. That's the current date, okay, since that date anyway. And I use 685 per million, right? This is called 685. Okay? Just use that. Okay. And I want to create 2 R object. Basically, 2 R object will contain this random forest fit. Okay. The first R object will be named iris RF1, okay, and the second object iris RF2. Okay. Well, this is one way to program. Of course, I'm not saying this is the only way. Okay. So here, and then I start with a training set. I also want to collect the information of the index for the training set. Okay. I start with nothing, and then I collect the rows by row. So there will be 2 rows in this case. We have two seeds. Okay. And I also record the test error. Okay. Test error here I record is a test error like this is numeric 2. So it will contain the test error for the first one, test error for second one. Okay. And here this is the loop that I look through this. So by the way, if you're interested in what this is about here, this is take any vector, it will generate sequence from 1 to the length of the vector. So it's very simple way to create a vector like this. Okay. Okay, and then here run in the for loop. Let me run this entire loop and just end right here. And I explain the loop inside. It's pretty fast, right? So we have everything. Here, this is random forest iris RF1. The seed value is this. I kind of recorded the seed value, and then here this is function call, and this out-of-band estimate error rate will be 3.33%, okay, with a test error rate of 6.7%. See, we have a trend set, of course, and we set aside trend set and test set. Finally, we predict a value, and then we have predicted this confusion matrix, okay, for the test set. We have this 6.7% for that test, for this test set, okay. And second one, random forest iris RF2. You can see that the error rate, the test error rate or generalization error rate is 5%. For this. And actually, this is done in this loop. Okay. It's pretty fast, right? Okay. Each one of these random forests has 500 trees as a default. We use a default value. I didn't change the default value. So we're kind of having for each trees that we try to set the seeds first. So set seeds I. Okay. So that will be the seed, and then we start collecting this ID tray. So we are actually binding. Originally start with nothing, right? Null is the beginning, and then here we just combine the rows. So combine the row that already exists with the current one run here. Basically, for each is done here. But this is overkill, so you don't need to actually use that. You can use the method I mentioned. We had example before. So basically, this is the same as you do something like this. This is the same thing like you do C sample 1 to 50. Well, in our case, we have sample size 30. Okay, and then sample 51 to 100, 30 of them. Okay, and then from 101 to 150. So actually, it's identical to this. Okay, except that I kind of demonstrate the use of for each. Okay. Actually, there's a better use of to fit in the random forest than this method. So I just try to use this as a demonstration. That. So actually, what I did is here for each say j from 0 to 2. So I'm going to add 50 times j later to that. This I sequence originally 1 to 50. And if j is 0, I add nothing to that. So that would result into 1 to 50, right? Okay, if j is 1, you have 1 to 50 plus 50. So basically you have from 51 to 100. So that's the basic idea within the sample function. And size, we repeat this p group size 33 times. Okay. So each one, the first run of sample will be using j equals 0, and then the size is 30. Second run using j equal 1 and size is 30. Third one using j equal 2 and size 30. So basically, same result as this. Okay. And here I call a combining function C here. So here the combine function is right here. So combine the result. Okay. And the operator here is this percent do. Okay. This is really interesting in the package. If you try to look at the vignette of this package, you can think about the use of that in the future. Okay. If you really want to run very extensive computation, you want to consider running in parallel. Because there are other betas packages that run the parallel computing in a better way. But this is really very easy to set up, okay? Like this, okay? And they did a commercial also. So if you look at the for each, because basically, look at that there, when we do this. Okay. See, when you load this for each, okay? This was originally created by the author of this for each, and later on, I think this is like when they send this package, including this one and the other package called iterator. This is used as sort of gift to R. Actually, this company they took R and commercialized. Okay, here this is Revolution Analytics. This is actually very dedicated software dedicated to data mining actually. Okay? And of course, everything is based on R, but they add a lot of this is kind of the optimizer and try to optimize the process, and they also use the most of the top tools in the fields and try to maximize this. Okay, I'm not doing conversion for them. Okay, they allows you to download for academic use, so maybe we can try this someday. I downloaded it, but I never installed it. I didn't get a chance to install that. They have this academic version. You can try it out. I saw in this webinar they did a comparison between this Revolution Analytics and SAS Enterprise Data Miner. Okay. What SAS Enterprise Data Miner is basically what they did. They try to fit all the computation into a single memory. You know, if you have huge muscle for that, you have very there are large memory to handle this. Of course, it's going to run fast. Okay? But they have proven using just a regular machines, even this. Okay? And if you can link like 20 such disk computers, you don't need to use more, maybe 10. I think they demonstrated 10. Like a logistic, they fit the logistic regressions of it's over, I remember over 10 million observations, and then like 7,000 variables in logistic regression. Okay. A regular machine like this runs 6 minutes with this R Revolution, and then if they put together like 10 machines, they run in like 44 seconds. It's really, really nice. They compare with that. Okay. The SAS would not allow you to benchmark their result. That's very, very hard. So they do something very similar to that. It's proven to be better than. Anyway, it's just if you're interested to download just academic version of this, you can try this one. Anyway, this Revolution Analytics, this is commercialized versions of R. This is completely based on R. You can try this out. Okay. So so that's the name for that company. Okay, Revolution Analytics. Okay. And from time to time, they also set up a few webinars. You might be interested in looking at that. Okay, where are we at? Okay, so here we talk about this. So I first create the ID of trains. I create and then I collect them in the sort of row. It's a row vector. Okay, so each one is row vector and create as rows. Okay, so then the train set would be just extracting this ID train. The I would be the current. This is the current run here. Okay? I'm going to show the ID train later, so you can see that. Okay? And test iris. Okay, this is. It's a two-row matrix. So after this run, you see that because we have two seeds here. Okay, so here this is the IDs for using the first seeds. Okay, for the train set. So we have 30 from first species, 30 from second species, 30 from third. Okay. And now here the second row corresponds to the second one. Okay. And what I did is here actually, when you want to run this sort of, in a sense, you consider when you do this photo, this is like in a sense like a batch run. It's not like you run this interactively. Okay. It's like a batch run of this. Okay, the key is using assign function. Okay, when you do that, it's like you're assigning this object. You're assigning this object into the name that we provided here. Okay, whatever that is, and this RF would be the name for these two objects. Okay. So after this is done, I also in this random for I also assign this into RF just for the convenience of trying to produce output like this. Okay, so after that, here this is just a message you want to communicate with. Okay, let's say audience. In this case, yourself. Okay. So here I set the seed values and then print RF. Remember, this is batch run. Okay. When you do batch run, you would not print by itself. So you have to explicitly specify, I want to print this one. Of course, there's a way to sort of override this default behavior. Okay? But I decided to do this way. So print RF. So here this is random forest like we have printed. The outcome from random forest. Okay. So it's print this part of the call, and then here this our back estimates of error, 3.33%. It's printed something like that. Okay. And then here we do predict. We can do predict on the test data set. So here we should predict RF and test iris. This is test data set, okay? For your current data sets anyway, okay? And type is response. So it will give you the classified group identities for the result. Okay? You might as well just use class instead of response. Okay? You can also use class. The newer version will just use response. Class is just to be compatible with older versions. You run with older version, you can use class there. Okay? So classify result, and later on we want to see the result from the test set. Okay? So simply we just produce this confusion matrix by tabulating actual identity for the test set against the classified identities for the test set. Okay? So basically it's done by this. And we print the result. That's why you see this one here. Okay? The result from test set. First part will be this. The first part will be this confusion matrix for the test result. Okay? And the second part of this is that we also calculate the test error and correct that in test error in a vector. Okay? So earlier I said this is vector length 2. Okay. So test error. Basically, you can take the confusion matrix, okay, and calculate the total of diagonal elements divided by the total of that this entire confusion matrix. So that would be this is not error, right? This is proportional correctly identified planes, right? Isn't it? And subtract this from 1, you basically get the error rate. Okay? And times 100. So here the test error will be printed like this, or print this result. So that's why the test error is 6.7%. I kind of put this all in this output. Okay? And in fact, we also create this test error here. Okay? We store that in there. The first one, test error is 6.7%, and the second one 5%, as you're saying in the output. Okay? Now remember when I did this, okay? You can see that there are two objects we get. This iris RF1, iris RF2. That's the result running this. Okay? Because I do this assign statements, the assign function. So let's say let's take the second one for now. I want to do further, okay, this kind of further operation on that. Okay? So here misclassified planes in iris RF2. You can also look at the probabilities for this misclassified identity. Okay. In the test data set, there are 3 misclassified planes. Okay. One from Versicolor and 2 from Virginica. So you can see that. Okay. So here, these are the probabilities. In fact, these probabilities in the random forest, the probability is basically this is just an average vote. Okay, on that, this individual. As you can see that. This is supposed to be Versicolor, but it got the highest average vote on Virginica. That's why we classify as from Virginica, right? Okay. And the other two is like the other way around. So these two are supposed to be Versicolor. They are misidentified as they are supposed to be Virginica, misidentified as Versicolor. And the second type of thing that you can predict all of this is like just look at the votes of all the observations in your data set. The key is this type equal vote. Okay, But by default is the votes will be normalized. So basically that will be the same as the probability. Okay. Without this, the result will be completely identical to that because actually that's that's a normalized vote. Okay. So that's why I say norm and vote equal false. You can also look at the number of votes out of this 500 trees. Okay. And this result. Okay. So here, you can see that these plants, okay, 71 got 439 votes out of these 500 trees, right? Okay. So that's why it's classified as a Virginica, okay? And here we have the majority votes on the versicolor, but in fact they are supposed to be from Virginica, okay? And the other thing you can look at is plotting this out-of-bag error rate, meaning that this is from the transit, this is not from so here this error rate will be from the transit, not from transit. This is not from transit. Okay. You can plot this result. Let me run this one and you can see that. Basically, you can take a look at the output here. So actually, when I run this, I run this plot the iris. So basically, this error rate. I also see it's also silently return a value this error rate matrix for all the 500 trees. Okay. Right here, I'm going to show the first 5 of them. Okay. So it contains 4 columns. First column, this will be the out-of-bag error rate. So basically, this is for the transit. Okay? And now here, this will be the error rate for each class. So here, this will be the class error rate. Okay? And the plot basically just a graphical representation of this matrix, 500 row matrix, this 4 columns. Okay? That's graphical representation of that. So here, for example, here starting from tree number 1, okay. So we have a big number here. Only the first, with the first tree we have this error rate like this. Can you see that? Okay. Okay, and then the rest are just flat. Okay, we didn't misidentify anything. Now here this is this out-of-bag error rate, and then. The green color is for versicolor, the class error rate. And in fact, if you look at the help documentations in this package, okay, you can do training and fit it on the test data set just in one step. You don't have to do this separately. Okay. In the for loop I did up there, I put them aside. So I first train the data, right? I train the model, use the train set, and then I predict the result for the test set. So I did it in 2 steps. Okay. In fact, in this function allow you to do just 1 step, okay, like this one. So training and then applying the train result to the test set is in 1 step. So basically it's right here, okay. So here this is random. Let me just run this result and then we can see the test error later. Okay. So here this is random forest and species model against all others, and data is our train set here. I use a train iris, right? Okay, this is our train set. And all you have to do is to just allow this random forest to test on that is by using these 2 additional arguments. So here x test, this is test iris -5. Column number 5 will be our target variable, so we exclude that from the measurement, right? Okay. These will be the feature vectors, or the input vectors for the test set. And the response is in column 5. Okay. Here this is data frame, and here this is a single column, it's a vector, so we expect that from test set. Remember, here X test and Y test both have to be from test set. Okay? And do this test and then we plot the result. Okay, this is the error rate. So now error rate has 4 columns again, but remember now the error rate, this is for test error. This is not for Auerbach error. And this is test error applied from the test data set. Okay. And now here these are the class error rate. Okay. For Sentosa, we actually didn't see any error, right? So there's no mistake. We have not misidentified any Sentosa plans at all. Okay. Like that. Okay, so the difference between these two is this. In this, if you look at this identities here, there's a particular components in this random forest object is this test. Okay, we can further look at that. Okay? Basically, the test result contain the predicted class, okay, and error rate. So actually, when you do plot that result, is take on this part. Okay, take the error rate and plot the result. Okay, you can actually see that. And there's also confusion matrix from that. You can extract that from the output. Here, volts and proximities. Actually, okay, they are all from that. Okay. And now, if you look at the original. Remember the last two, we do random forest on the train set first, and then we apply that on test set. So here, this is a bit different. Okay, this will contain no information on test because we do it separately. Okay? That one we only have information on the train set. Okay? But when you put this together with the test set, you will see this result. That's like the one we see here. Okay? This iris RF will contain the training information as well as the result from the test set. So that's why you have this result from the test with this error rate right there. In fact, you can extract this information. You can extract confusion matrix of this. I think that if you look at the package Caret, they do have this extraction function called confusion matrix. If that is attached, I think you can do that. I simply just extract this component out looking at this result. Okay? Now you know where to get the German credit data set. It actually appears in several packages, including this one. Okay. The German credit data is from this package called EV3. This evolution tree. This is constructed by the same author for the party package. So all you have to do is just attach that. So currently, this is in our current list of data. You don't see this German credit data set until you attach them. Okay, use a data command. Okay. You can see that we have this German credits attached somewhere right here. Right. Okay. So German credits now is just part of your data set. You can see the class there. Then at the time you're trying to work on case study 2, I ask you to basically define clearly which variable is vector, which is numeric, and which one is order data set, the order categorical variable. In fact, this is strictly defined. Okay, as you can see, many of these input variables are vectors, including one. This employment duration is actually order categorical data. It's very important for tree model that you set this correctly. It's supposed to be order categorical. So it's only called for, say, a number level -1 split, possible split. Okay? But if this is not order, you have to do the number of levels -1 and then -1, that many splits. Okay? So actually, there's a difference between this. So all this, you can see that all the variables are correctly set with whatever types of variable they are supposed to be. Okay? Duration is numeric and the amount is numeric. I think only quite a few numeric, the rest are vector installment rate, numeric. This present red is residence. Is that numeric or not? Anyone recall what that is? Is it a vector or numeric? Huh? It's supposed to be vector, right? So I probably they made a mistake here. They changed that to vector, I think. Was it vector? I couldn't recall what that is. But anyway, we can go back and check. But let's say let's accept that as is for now. Okay, and we go back and check whether this is correct. This is I suppose they did it strictly. I'm not sure what happened to this. Okay.
I guess that's years
Huh?
that you've been in your current
So years, right? So it's supposed to be numeric, isn't it?
if I remember correctly, should be the years of your present. Like what year you've been there in your current present.
Oh, okay. So numeric makes sense, right? Isn't it? Or not? Well, anyway, we have to go back and check with this one. But a lot of these are supposed to be vector, so you can see that they are correctly set as a vector, including the credit risk. That's our target variable. So now we can look at this one. Here in the future, we try to analyze on German credit data set. It's right here, okay? Right in this EV3 package, okay? So actually, and you can see that, of course, I already mentioned there's. Suppose let's look at those with bad credits, the IDs in this data set. I think they kind of mingle. They didn't put like first 300 observation being good credit, bad credit, the remaining 700 with that. So kind of mixed. Okay. So you want to just separate them. Okay. The easy way to do it is just do that. Okay. So here, bad IDs is with this German credit and which credit risk would be bad. Okay. So just give you ID for that. Okay. And then 1 to, in this case, 1,000, right? 1 to 1,000, this is number of rows, German credit. Okay, and subsetting this by removing this bad credit IDs and the result is a good credit ID. You can actually see that. Okay, oh, forgot to run this with ID. So here, as a first, by example, okay, these are the bad IDs, right? The IDs for the bad credits. Okay. Anyway, let's say that we want to do like 60% split in the trend set and test set. Okay. And trend sizes will be done by this, right? I think it's very easy to fix. So here, trend size will be it's just cross table and create this credit risk that we have that 700, 300 times the proportion of trend. You get the right result. Okay? Just want to make sure the result is integers. I use a floor function to extract that. Okay? So 420 and 180. So this is supposed to be the sample size we try to do. Okay? So now let's look at this one. I already did that. Okay. So here, this will give us an ID for the trend set, right? Okay. All we have to do is just sample from those IDs for the good credits, and then even the trend size, right? 420, and sample from the bed IDs. Right? So that will give you this ID for that. I do sorting after that anyway, so the result be the correct one. And now we create this trend set and test set for this German credit. Well, this result, if you use a random forest, I think look at the result. The result is not really good. You see this result. Well, maybe I didn't pick the good seeds to start with. We need to try several. But with these two different, you can actually try different seeds. Okay, I didn't do it here. Okay. Just want to show with without setting the priors and costs. Okay. The first one is here we run the first one without setting the. This is first one without setting the cost, without considering the priors and the cost. Okay. So you can see kind of out of bank estimates of about 23.67%. And test set error rate is 24.75%. This is especially bad. In fact, here what happened here is that they actually misidentify the bad credits as good credits, which is really bad, right? In this case, right? Isn't it? There's a cost of about 5 to 1 that this could occur. If these two are switched, then that will be better. But this is not the case. The result is not really good. Okay. If you try to very ballpark estimate about the cost, you can use 5 units of 81 plus 1 unit is 18. This is it's over 400. It's really bad result. Okay. Now here we do random forest with 500 trees. Maybe you want to try more trees to start with. Okay. Anyway. Now let's try to incorporate the priors and the cost in there. Okay. Remember that we have with German credit, we have 5 versus 1. Okay. Of course, when you misidentify bad as good, okay, and you misidentify good as bad, it's only 1 unit, right? This is the cost. Okay. So basically, we create this. This will be the weights that we're going to consider. Actually, you don't have to put the weight integers. Any integers will be fine. Okay. So actually, what they did is like internally they add this up and divide. They use this number divided by total. So basically, to give you the correct result. So it's like the first one is like 7 out of 22, and the second one 15 out of 22, right? Okay. You don't have to change this. Just use that as a weight. Okay. So here, this will be the weights we use. And let's run this random forest with this weights here. The idea is with this additional argument, right? So it's specified. Okay. Here we specify the class weight will be this. Okay. I try to. I'm not supposed to do reverse. Okay. But the reverse is just still the same result. Okay. I shouldn't use a reverse. Reverse will be different. Let me run this again. So now you can see that with these priors and the weights considered, the test error is 23.5%. Looks like slightly better than this one, or probably almost identical, right? Okay. Except that here we see that even worse. We have slightly better actually. Okay. But still very bad on that. Here there are 82 bad credit were misidentified as good credits. It's really bad. Really bad result.
Is it just because of the seeds?
Well, not necessarily just because of seeds. Sometimes this model would not fit nicely on that. We can also try, there are some other parameters. We can also try number of trees, right? Let's put it to 1,000 and see what happens. Okay? And probably try to change different seeds. And remember, in our class now we mentioned this is only a random statistical method. Okay? So you should not rely on just result one. Okay? So you have to just go over different seeds and see what happens. But in both cases, we end up with very bad result. So a lot of misidentified bad credits. They're supposed to be bad, but we identify them as good. Right? Okay. It's really bad. Okay. Now here I show example of extracting this information from the test. Okay. Here extracting the confusion matrix of that out of that. Okay, that's basically what we have up there already. And here actually what was shown is the error rate. This is error rate for individual tree. Let me try to run some sort of the. This is not really moving average, but this is cumulative average. Okay. So cumulative average means that I first look at one tree, and at tree number 2, I look at these two trees combined and see what is the error, the combined error rate. So I take the average of error rates from these two, and do this in sequence up here until we include all the 500 trees and see what happens. Okay. So here basically let's do this apply function. So I take the error rate from the data set. This will be the test error rate, right? This is the test error rate, okay? And apply. Well, actually, this is the column matrix as we always said before. We wonder what this is. Let's just take a look at the first few observations from that, okay? And look at this. Let's look at this like the average error rate, cumulative average error rate in this way. Okay. And here I do this apply function. I basically use this cumulative sum of that and divide it by the current number of trees already included, right? The sequence alone. That. Does it make sense? No. Why not? Well, here R has this all kind of apply function which are very powerful, so you can apply. So any parts of your margin in your data object with a specific function of interest like this one, I do this cumulative average of that. Okay, so I use cumulative sum divided by the number of observations encountered so far. So that will be the sort of cumulative average. See the result. Okay, and put the result in this GCR FG. Let's say I do that. Okay, and then I do this matrix part and see what happens. You can see the result is really, really bad. Okay. Here there are three lines here, right? Test and good credit, bad credits. Okay. So this would be gray color, red and green. Okay. So you can see that the decrease in this average error rate for the out of back error, right? That means that more trees is better, of course. Okay? And also true for the good credits, right? Okay, but not for the bad credits. This is quite a surprise. Maybe this is not a good model at all. So. If you're interested, you can also look at some other. Here, let me just run this. This is from party package. And then I run this conditional random forest. Okay, with 1,000 trees here. Okay, let me just go through this later. It's going to take a while to run this conditional random forest. So here, so basically what we have, or we still start with the random seed to start with. Okay. And then here we run on this party package, we run on this this conditional forest, okay, C forest, and then credit risk model against other, and here is our transit, right? Our transit, and then there are control parameters of that is done by this, okay? And there are 1,000 trees and number of variables included in each tree to try the starting value to try it before, okay? So start out with the trees with 4 input variables, okay? In this trial, okay? And then on we get the tree response. Here these are some the response on each individual tree. This is the way you can extract the information from each individual trees out of this forest, okay? It's going to take a while to do that, okay? And here, the result of this tree response is going to be a list of, in this case, supposedly 1,000 trees. But not all trees will be meaningful according to this analysis, so it's only a subset of that. Okay? And we extract the first components, basically those are the so-called good, right? Class as good one. Okay? This is the response on the tree. This is some kind of measurement, okay? And you can use this measurement to turn that into like what was that? This is area under the curve. This ROC. I'm going to mention about that. Okay. What was ROC curve? ROC is what sensitivity versus specificity, right? SEM versus SPEC, right? Specificity. Okay. And the area under the curve actually give you an idea of the goodness of that, okay, of the performance. Unfortunately, it's taken too long. I probably shouldn't run this. Okay. Anyway, so basically, I extract the information from that, and then here, this is a way to try to do some kind of inference. Okay. Takes a long time to do that.
I think you need to do the legend on your graph first.
Oh, yes, I forgot. Oh, under. I'm waiting. I forgot. So I already forgotten about that. Yeah, that's the previous run. You're right. Okay. Because I used locator.
Yeah.
I forgot about that. Yes. Thank you. Yeah, and word. It's taking a long time even. We are at this tree response anyway, so here we are good. Okay. So basically, this German credits give you this C statistics. Basically, is this area under curve, 92%. That's really good, right? Supposedly. I think I have this reversed. No wonder this looks strange. Okay. The result is supposed to be bad, not good actually. Here, I think I shouldn't use this. This is supposed to, yeah, this is wrong, sorry. The last one was wrong. It's supposed to be this, supposed to be a very bad result. Okay. Here we run this. The result C statistic, the larger the better, basically this is like area under the curve. And then we have only 7%, because this is not really good. And there's a statistic sort of related to that. Actually, this is some kind of measurement of difference between concordance and discordance. Basically, this is the regression coefficient, okay, for that thing. Okay, it's a D statistic. This is called Sommer's D statistic. Okay. D statistic. This is slope. Basically, this is a sign of say yi minus yj versus So we look at the basically this is this is measurements of say concordance minus discordance. The larger the better. That means that they are in more agreement than that. And negative value is really bad, right? Means that you have a lot of discordance in the result. Someone used this statistics, tried to value the result. It's kind of interesting. And here, this statistic, this summers, these statistics can be extracted from this package. And here we just did this one-time deal, so I didn't attach this package. Let's use that. I think I used up time, so I will continue on this one, and then we will talk about partial least square next time. And after that, we will talk about unsupervised learning.
Yeah.